Hello, students. I hope you got a lot of rest last night, ladies and gentlemen, because you are going to need all of your energy to work our way through this topic today. So, what is our topic? As you may have guessed, our topic today is energy. So let's get right to it. As you are opening your books to your notes page, let's talk about energy. Energy. So, as we're opening our books and getting ready, let's just talk about this question for a moment. What is energy? Well, you came up with some really good ideas, but we're going to summarize all of your answers into one phrase. And we're going to say that energy is the ability to do work or cause change. In fact, I think that has a nice little rhythm to it. Energy is the ability to do work or cause change. In fact, let's say it together, shall we? I think we can turn this into a class-wide chant so loud that they'll be able to hear us down the hallway. So let's say it together. Energy is the ability to do work or cause change. Again, energy is the ability to do work or cause change. One more time. Energy is the ability to do work or cause change. I'm going to have that catchy little tune in my head the rest of the day. I don't know about you, but instead of clapping, we could stomp our feet and try it again. Energy is the ability to do work or cause change. So let's take this definition of energy and expand upon it a little bit this period. I want you to remember when we use words in science like work, we're talking about something very specific. Remember what work is? What is work, everybody? Perhaps you remember work is equal to force times distance. And remember what a force is? What is a force, everybody? A push or a pull on an object. So, again, when we're thinking about science class and physics in particular, and we come across these different words, I want you to automatically associate these words with their scientific meanings, and then we can build upon it even more. So, again, energy is the ability to do work or cause change. Work equals force times distance. And there is a unit of energy that we use, and it is called a joule. Should sound familiar to you. A joule. By the way, anybody remember what a joule is equal to? Hopefully you said a Newton meter. So the unit of energy is a joule. Now, we have identified different forms of energy. And so today we're going to talk a little bit about the different forms of energy. In particular, we're going to discuss 5 different forms of energy, and we're going to give some video examples to each one as well. So let's get started right away with number 1. Number 1 is mechanical energy. Mechanical energy, think of the letter M, begins the word mechanical. It also begins the word matter and motion, because mechanical energy is in fact matter in motion. Some simple examples of matter in motion. Woo-hoo-hoo! A ball being thrown up and down or bounced down and up. Balls, great example of mechanical energy. Riding a bike, another great example of mechanical energy. Cute little robots like this. Ah! Oh boy. All right. Mechanical energy. We'll get to those later on. Running. Great example of mechanical energy. The blood coursing through your body with all of the little red blood cells, boom, 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 as they move around. Matter in motion, mechanical energy. I'm going to use one more example here. In a box of matches, and I could take a match out of the box. Hey, that was an example of mechanical energy too. If I were to move the match over the strike plate, that would be an example of mechanical energy also. We'll get back to these in a moment. But you get the idea. Mechanical energy, matter in motion. So, when you think of matter in motion, does anything come to your mind? Well, let's watch a little video here about matter in motion. I love these 360 videos. By the way, if you tend to get motion sickness, you might want to look away from the screen right now as we go for a little roller coaster ride. Here we go. Filmed 360 camera. By the way, I can control this camera. Which way do you want to look? We can look up or we can look down. How about we oh, let's look at, check out the view top of the roller coaster. My goodness, we are going pretty high up. Really high up. Let's look around. Look at the view. Oh my goodness. Oh my goodness, we are really high up. Oh, we're almost ready to come down. Whoa, whoa, whoa. Happening to the like roller coaster. Yes, yes. Whoa, 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 whoa. I can feel the G-force in motion. Oh, whoa! Going too fast? Coming in. Oh! Get over there! Who's over there? Woo! Oh, I'm gonna toss my cookies! Woo! Oh, yes! Is it almost over? Is it almost over? Oh! Oh! Okay. All right. Feels like we're slowing down now. Whew. Great example of mechanical energy. Energy in motion. Let's move on to the second one, shall we? Number 2. Whew. Building up a sweat from that roller coaster ride. I'm getting a little bit hot. I think that mechanical energy has transformed or transferred into energy number 2, which is heat energy. Heat energy involves motion again, but on a much smaller level than atomic motion. Some examples of heat energy include melting and evaporation. Another example is, well, take your hands together here. And on the count of 3, clap your hands as hard as you can and then rub them together for 10 seconds. Are you ready? 1, 2, 3. Boom! Rub them together. Rub, 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 rub. While you're rubbing them together, that is an example of mechanical energy. Now, when I tell you to, put them on your face real quick. Ready, set, now. Oh, can you feel the heat today? That heat energy is a result of the mechanical energy transforming into heat energy. So let's check out an example of, oh wait, one more thing I want to show you here before I show you the video example. Let's go back to our match again. If you take a match and mechanical energy moves it across the strike plate, when you do that, it actually causes a lot of friction, just like when you were rubbing your hands together. And when there's friction between two objects, what do you think the result is? Heat energy. That's right, heat. So we'll get back to these in a moment again. But let's go to our video example of, a big example of heat energy. Check this out.
Yellowstone National Park could be sitting on a time bomb. There is a supervolcano underneath the national treasure that's more than twice the size of the park itself. The U.S. Geological Survey says the volcano last erupted 630,000 years ago.
And visitors of Yellowstone National Park have been advised to keep off the roads. That's because the heat from a supervolcano beneath the Earth's surface is melting away the asphalt. Park officials have closed the 3-mile-long roadway known as Firehole Lake Drive and have asked visitors to park on the sides of the road. Park officials warned that stepping on the seemingly solid asphalt could create an illusion, and you could quickly find yourself stepping into hot water.
Literally. Wow. It's so hot. There's so much heat energy. The road is actually melting. My goodness, that super volcano. I hope it doesn't erupt anytime soon, because that volcano is massive. This is basically the size of the whole park. I don't know if any of you have ever been to Yellowstone National Park, but that's one big park. I'd hate to see it go up in smoke from a massive release of heat energy. Oh, boy. All right, let's move on to numero 3. Number 3. Number 3 is chemical energy. Chemical energy involves something on a small scale again, the atoms, whatever they are, and we'll learn about those in the near future, but it involves atomic bonding. Some examples include burning, chemical reactions. Let's go back to our little match example here, okay? We take our match and we apply some mechanical energy to the strike plate. That mechanical energy is then converted into heat energy from the friction. And when it reaches a critical point, that heat energy causes a chemical reaction, which results in the release of chemical energy. Would you like to see it, by the way? Ready? Give me a 3, 2, 1 countdown, everybody. 3, 2, 1. You see that? Look at that. You are looking at chemical energy here, everybody. You are looking at chemical energy. And thankfully, it's far enough away from my face that I'm not burning myself here. But I better be careful, because that chemical energy, I don't want to get too close to my finger. Woo, woo, woo. So I'm going to put it out right now. There we go. But that chemical energy from the heat energy from the mechanical energy. Well, let's see another example of chemical energy with a chemical reaction. And check this out. Every so often, NASA launches rockets into space to carry things up to the International Space Station. And not too long ago, one of these Antares rockets took off from Wallops Air Force Base in Virginia. And even here in New Jersey, we were able to see this rocket's red glare almost bursting in air as it proved through the night the rocket was still there. But here's the final countdown. It's the final countdown.
3, 2, 1. And as you can see, Cygnus lifting off on top of its Antares rocket on its mission to
It's
deliver
chemical
supplies and science to the
energy.
International Space
That's
Station.
chemical energy, everybody. Oh yeah, check it out. You have to pay attention to the news next time one of these launches from
First stage is
Virginia.
now
If
burning
the
and will
weather
burn for 3
conditions
minutes
are
and
right,
20 seconds of
we can
flight
actually
before
see it
cuts
from
off
here in
at,
New Jersey in the night
just about
sky,
3.5 minutes
assuming
into
they
the flight.
launch it at night like this
That
one
provides
was.
the initial thrust to get
Yeah,
Cygnus going
that
on its
is pretty cool. That is pretty cool. So let's go to number 4. Whew, it's very energizing. Number 4 is electromagnetic energy. Electromagnetic energy is the result of electrons in motion, or in other words, moving electrons. Some examples of this include, well, electricity, turning lights on, electric motors, and I got the hiccups. Your computer. By the way, hiccups are not an example of electromagnetic energy. Tell me, what form of energy do you think hiccups are a form of? Mechanical energy. And I think they're gone. Whew. Okay, good. All right, let me show you another example of electromagnetic energy. I'm going to go back to the box of matches. I'm going to take a box of matches, open it up, take a match out here once again. Oh, let's take one with a big head. Here we go. Okay, so we got a match. We got a match box with a striker here. We're going to apply mechanical energy to the match on the box. That mechanical energy will transform into heat energy, warming up the chemicals on this match head. And when it reaches a certain critical point, that heat energy will then be transformed into chemical energy, as we saw before the ignition of the match head. But how were we able to see it last time? Well, you were able to see it because it's giving off light, which is what it's doing right now. This is a form of electromagnetic energy. And it's getting, ow, a little bit too hot for my finger. Okay. Electromagnetic energy is the release of moving electrons. It's moving electrons, and we were seeing that in the form of light from the lit match. So just a simple match can show us the transformation of energy from one form to another form of energy. This is going to be really, really important for us to remember in the very near future. So let's give another example of electromagnetic energy in the form of a powerful release called lightning. Let's check this out.
Lightning strikes from storm clouds down to the ground. It also strikes up into storms and also out into thin air. Sometimes isolated sparks shoot up out of the ground. Lightning channels sometimes sail in strong wind and take bizarre, unlikely paths through the sky. This video is about the weird behavior of strange lightning.
That is pretty cool. That
Most of us have seen epic lightning bolts branching from the cloud down to the ground, but have you ever seen lightning bolts branching up? Upward moving lightning, or ground to cloud lightning, often has a strange, smooth, and fluid channel. This type of lightning was extremely rare prior to the Industrial Revolution and is said to have only occurred from mountain peaks. Tall man-made structures help trigger this discharge, and increasing skyscrapers and radio antennas are making this brilliant phenomenon more common. Most lightning discharges occur only in the clouds, never striking the earth. This is called intra-cloud lightning. But sometimes it leaps out into the naked air, and so this phenomenon is called cloud-to-air lightning. During a lightning storm, it's a good idea not to be the tallest thing standing around, but that doesn't mean you're safe if you're the shortest. Lightning seems to have a physics-defying mind of its own and often takes unlikely, erratic paths before striking a random target. Milliseconds before a typical lightning strike, a stepped leader advances from the cloud to the ground. Before reaching the ground, a charged ionic channel called an upward streamer reaches up to meet the leader. When they connect...
Yikes. And if you want to see the rest of that video, which is super cool, head back to the notes and you'll see that. But let's move on to our next form of energy, which is nuclear energy. Nuclear energy in the form of either fusion or fission. And I'll briefly touch on these two words here, fusion and fission, although later in the year we're going to spend a whole week on nuclear energy and we'll unpack those words a lot more. But fusion is when you've got two or more smaller atoms joining together to form a larger atom. That's fusion. Fusion is together. Fission is what happens when you take a big atom and you split it apart. That's fission. Fusion, fission. Our sun and other stars utilize fusion nuclear energy. You've got lots of hydrogen atoms coming together under incredible pressure and fusing those atoms together, releasing an enormous amount of nuclear energy. Atomic bombs, on the other hand, atomic bombs take big atoms like uranium of certain isotopes and split them apart. And in so doing, it releases, again, an enormous amount of nuclear energy. So let's check out a video here about nuclear energy. I can't demonstrate that to you with a match. Sorry. But let's check out and watch this one closely. I'm going to let this one run all the way through. The frame of reference is incredible. So watch this video because I want you to get a sense of how energized, how full of energy nuclear energy can be. Here we go. Relatively small, but you wouldn't want to be. That's a neutron bomb. That's the size of the bomb that dropped on Japan to end the war. And that was the second one. That's the deadliest bomb we have in our arsenal of nuclear warfare. That's the most powerful bomb ever created. Did you catch that? Mother Nature is getting more impressive. Golly, that would be awful. Super volcano, like, oh my, like Yellowstone. Oh boy. Half of our population would be wiped out immediately. That would be rather frightening. So if the super volcano in Yellowstone erupted, you'd see it from Earth. And yet, there's worse. That's what caused the extinction of the dinosaurs. An asteroid impact. Oh my. That's a lot of energy. For now. It's like the Death Star on Star Wars. But it's a gamma ray burst caused by the hypernova of a nearby star. Everything in its way will vaporize. That would be powerful. A planet killer. It's the most powerful explosion in the whole universe. That would be pretty freaky. But even on a relatively smaller scale, the nuclear energy that we are able to release is enough to wipe out a lot of people on our planet. So we're going to call it there on that happy note for today, the 5 forms of energy. So until tomorrow, I'll say bye-bye.